Day 46, page 975, problem 21. This is very similar to the last problem. Once again, let me fix the terminology here. The x over here should be an L, and these y's are x's, x sub 1 and x sub 2. And we're looking for the, once again, the fourth maximum. I'll go down to the lower part here this time just to show you. It doesn't really matter which one you go to. You have, well, the one at the top, which we did in the previous problem, that's the fourth order maximum. At the bottom here as well, that's the fourth order maximum. So we're looking for x, x sub 4. I'll label it on the bottom one this time. How far that is. But now I'm going to use the second equation. I will need to use this equation this time, which only gives me an approximate answer because it depends on small angles, because we're using the small angle approximation that sine theta is roughly equal to tangent theta for these small angles. But it will be close enough to give us the idea. And we're looking for x, and I think they give us everything but x. So, for example, I'm going to plug in x equals, we're looking for, that's the fourth one, number 4, fourth order. Lambda is blue, 487.99, 487.99 nano, so don't forget to put times 10 to the negative ninth in your calculator. L is how far away the screen is, 1 meter, 1.00 meters, divided by D, 0.2 millimeters, so that's 0.0002 meters. Got to make sure you're in meters, or if you want to put 0.2 times 10 to the negative third meters. So that should give you the answer for x. Now, just a kind of a little bonus here. It looks like if you continue on here, the fifth interference maximum is going to be gone because they're diminishing here. And then possibly the sixth would appear again, kind of like the fourth one, maybe look at the same brightness as the fourth one. But let's just say, for example, that the fifth one is gone. That would coincide with the that fifth interference maximum, which is not appearing, is more or less coinciding with the first diffraction minimum. So if I go to my diffraction equation, there's two of them, D, which capital D, sine theta equals m lambda, or x roughly equal to m lambda L over D, where capital D now is the slit width. I could actually figure out the slit width here, because I'm assuming, well, L is the same. For example, I'll have an x figured out, so I'll have x from the first part. So what I'll have, using the second equation now, I would have x, so I'd have x, m would be 1, that'd be the first order minimum, and I know lambda, and I know L is 1, lambda is the 487.99 nanometers, so I would know all of these. So the only thing I wouldn't know is D, so I could use that equation now to figure out D, how wide each of those two slits are in the diagram. I can go over to the diagram to show you, it's hard, but this little slit, that space in there, is capital D being how wide that slit is. Not how far apart it is from one slit to the other, but how wide each individual slit is. Once again, with that particular situation, M would be 1. That's the first order minimum, which coincides with roughly the fifth maximum, but the fifth maximum therefore does not appear because that diffraction envelope then basically causes that fifth maximum not appear. It causes all the diminishing of the brightness of these maximums.